Okay, we're doing P-Adic numbers today. This was in my last video. I didn't know what they were, so we're going to just look them up right now. So we're just going to go to YouTube, look up the first video, watch it. Oh, my Markiplier. Oh, Gotham chess. All right, P-Adic numbers. Oh, fun fact, the other night I tried watching this in my, like before I went to bed. I did not get this, so we're going to try yet again to understand. I guess we're going to watch this one called 1 billion is tiny in an alternate universe, introduction to P-Adic numbers. Hopefully that's how you say it. I don't remember. But yeah, let's just get into it.
You're familiar with the powers of 2.
Oh wait, I need my notebook.
But you may not know about a hidden pattern lurking in their digits.
I want to know the
To see it, let's get some.
I'm sorry, I missed it.
Let's also align
What happened?
the digits.
What happened? Go back. Sorry.
You're familiar with the powers of 2. But you may not know about a hidden pattern lurking in their digits.
Oh my gosh.
To see it,
It's Morse
give
code.
each of the digits 0 through 9 its own color. Let's also align the digits to the right. This way, all the digits in the ones place are in the same column.
It's a game of Tetris. It's actually Tetris. P-Adic numbers are just Tetris backwards.
The tens place
I'm
are
a
in the
mathematician.
same column, and so on. Now let's add a few more rows.
Holy.
Overall,
It's a
the structure
triangle.
inside this triangle looks pretty random. What
Wow.
if we just look at certain rows?
Kind of looks like sherbet ice cream, low-key.
Here's the first row, 10th row, and 100th row. Here's the 1000th row. This number is too big
Holy,
to fit
that's
on the screen,
a big
so
number.
I chopped it off after about 30 digits. Here's the 10,000th row. And here's where things get weird, because watch what happens when we add more rows.
Oh my goodness. They're numbers.
Let's include some more data.
Interesting. Oh, look at the right.
This is suggesting.
Look at this, John, right here. Oh, I'm already picking up what they're putting down. I know what's going on. Something's fishy. Something's fishy
that
here.
The last few digits of 2 to the 10 to the n plus 1 are exactly the same as the last few digits of 2 to the 10 to the n. And as we increase n, the agreement gets better and better. In other words, in some weird sense, these numbers, these large powers of 2, are converging to something.
Interesting. Converging to something.
Of course, they're not converging in the usual way. 2 to the 10 to the n doesn't converge to anything as n gets large. It diverges to infinity. So what on earth does this sequence of digits represent?
Math is wrong. That's what that represents. It's all a lie. Albert Einstein, idiot. Oh, that guy is so stupid compared to my intellect, my genius intellect.
Did we just discover the secret digits of infinity?
Yep.
No, we discovered a number that belongs to a different number system than the one we're used to. What we'll see in this video is that if we change our ideas about which numbers are small and which are large, then we get a new number system where this infinite-looking number actually makes sense. This new number system provides an alternative to the real numbers, and there are good reasons to use them instead of real numbers in certain situations. Before we go on though, let's take a minute and remember why we like the real numbers so much in the first place.
We
For
do.
one thing, we can easily picture real numbers as points on the number line.
That makes sense.
The real numbers contain all the integers, as well as all the rational numbers. The real numbers support addition, subtraction, and multiplication. They even support division. They also contain all their
Why is division a separate thing? Maybe, I guess division has its own weird properties and quirks, so
limit
I don't know.
points, which is a way of saying that there are no holes in the number line.
Fair.
Real numbers don't have everything we might want from a number system. For example, they don't contain square roots of -1, but they're pretty good. On the other hand, the real numbers aren't the only game in town. There are alternatives that have many of the same useful properties, and even have some properties that the real numbers don't. Some of them even contain square roots of -1.
I'm kind of trying to visualize right now, like what a set of numbers not being able to contain a number line. Like, what does that even look like? You know what I'm saying? Interesting.
These are the systems of P-Adic
Interesante.
numbers. P will end up being a prime number, so there are the 2-adics, the 3-adics, and so on. Are these good names for number systems? Well, no. But if we're honest, neither is the real numbers.
Okay.
To understand P-Adic numbers, let's start with powers of 10 rather than powers of 2.
So these would be the 10-adic numbers.
Eventually, every digit becomes 0. So in some weird sense, 10 to the n is...
Wait, low-key, this kind of reminds me of the the stairs on Mario before you hit the flag. Did you know like Mario speedruns are literally like to the T? They're so optimized. Like I think they like every month they're like, yo, the what is it? The record is it 343? I don't know. They're like the record's gonna be broken by saving like 2 frames, and you're like, bro, what? They're lying. There's no way. Anyway, I thought that was interesting.
Is getting closer and closer to the number with all of its digits equal to 0, which is 0 itself. Since powers of 10 are close to 0, that means they're actually small numbers. We can make this precise by defining a new absolute value. Determine the highest power of 10 that divides a number. Then divide 1 by that power of 10. This is its 10-adic absolute value. For example, 78,000 is divisible by 1,000, but not 10,000. So its 10-adic absolute value is the real number 1 over 1,000. What is the 10-adic absolute value of 1 billion? 1 billion is divisible by 10 to the 9th, but not 10 to the 10th. So its 10-adic absolute value is 1 over 10 to the 9th.
Okay, so I think, to kind of recap, right? The staircase was talking about like visualizing how 10 to the 9th power is closer to 0 than it is 1, right? Because you have all these leading zeros behind it, so thus it is like closer to 0. And I think, right, this is just talking about how to kind of visualize that in an intuitive sense, right? So to find how close a number is in a 10-adic, I guess, base number system, you put 1 over the highest power of 10, or the adic number you're dividing by, and that divides n, and thus it shows how a smaller number like 78,000 is bigger than, what is this number? 1 billion, right? Right, 10 to the 9th is 1 billion. Sorry, I was looking at the zeros instead of the 9. So, yeah.
The usual absolute value, which corresponds to distances on the number line, gives us one way to define the size of a number. The 10-adic absolute value gives us a different way. In each setting, numbers whose sizes are close to 0 as real numbers are, by definition, small in that setting.
I guess this makes sense too, because by dividing by the largest number of 10, the largest power of 10, like look at 78,000, right? 78,000 is divided by 1,000 because that's how many zeros are there. And kind of like that analogy before is like the more zeros, the closer you are to 0. I find it more intuitive that way. Just thought I'd say.
So according to the 10-adic absolute value, 1 billion is a tiny number. And as you take larger powers of 10, you get even closer to 0. But wait a second. If we're talking about a billion things, for example, a billion ants, that is not a tiny amount of ants, right? That is a lot of ants. This is only 1,000 and it's already a lot. But the thing is that we're changing our fundamental definition of size. Our usual ideas of large and small are tied to the real numbers. So if we choose a different notion of size, then large and small have completely different meanings. The real absolute value nicely corresponds to distances on the number line, where two numbers are close when their first several digits are the same. But the 10-adic absolute value has nothing to do with the number line. Under the 10-adic absolute value, two numbers are close when their last several digits are the same. And by this metric, 1 billion and 0 are actually pretty close, because they agree to 9 digits. This is a good thing too, because it means that there's hope of actually making sense of infinite sums.
So quick thought idea. So does it matter where the zeros are in the number? Like if there's 10, or there's 8 zeros, but they're in different places in two numbers, right? Like which one is closer? Are they equal? I don't know.
Like the limit of 2 to the 10 to the n that we discovered. It's not infinity, it's a 10-adic integer. A 10-adic integer is a sum that looks like this, where each digit d0, d1, d2, and so on is a number in the range 0 through 9. For example, the limit of 2 to the 10 to the n is the 10-adic integer whose digits are 6, 7, 3, 9, and so on. Every positive integer is a 10-adic integer, because we can extend its base 10 representation with zeros. Just like we can make sense of this infinite sum in the real numbers, where powers of 10 get big, we can make sense of this infinite sum in the 10-adic integers, where powers of 10 get small.
Okay, so this makes sense. The bottom part here, right? This is pi, because each, you add 1 over 10, so it's like going to the right each decimal place. this side is kind of doing the opposite thing here. It's taking 6 and then it's multiplying by 10 to the next power, kind of building up this big number. So it's like, if anything, it's kind of like the opposite of finding the smallest decimal place of pi, if that makes sense. Like pi, we're trying to go to the right. We're trying to find what the smallest decimal is. I don't even know how many known decimals of pi are there. Like, I feel like I should know this. 300 trillion decimals. That's cool. So that's pretty impressive. So it's like kind of trying to do that, except the other way, like in this big 2 to the 10 to the n number, right? That's a huge number. It's like, it's massive. So it's like trying to find a sum to get that number, which is interesting.
If we want, we can make the digits easier to see by putting the powers of 10 in the denominator. We have to introduce negative exponents to do this, which
Honestly,
looks a little strange.
I found that other way more intuitive. I don't know why.
But now it's closer to the representation of a real number. So we know what a 10-adic integer is. It's essentially an integer, but where you allow the digits to keep going infinitely far to the left. Now we can revisit our table of properties and ask which properties hold for the 10-adic integers. But here's the bad news. There's no 10-adic number line. You might try to build
Dang it! No, my only wish for Christmas. Oh, mercy.
one, say by placing 1,000 close to 0, and then 1,000,000 even closer to 0, and 1,000,000,000 even closer than that. But the problem is that different 10-adic integers can have the same size.
That's crazy. Like
For example,
infinity would be close to 0.
78,000 has size 1 over 1,000, but so does 35,000. Which is bigger, 78,000 or 35,000?
Oh, this is what we were talking about.
So we can't place one to the left or right of
They're the same size. They're the same size.
the other, and there is no 10-adic number line.
Well, I gotta check my audio. When I touch my mic, sometimes it freaks out. Oh, we're chilling. We're chilling.
Since there's no 10-adic number line, there are no notions of positive and negative. This lack of a simple geometry makes the 10-adic integers counterintuitive. So we'll need to rebuild our intuition before we can maneuver comfortably in this bizarre place.
I'm comfortable.
This is one of the most
Wait, what's your name, dude? Sorry, I need to know your name. Eric. Yes, Eric. Eric, I'm so comfortable right now. You have no idea. Maybe a little too comfortable.
exciting things about mathematics. With enough exploration, we can learn to find our way around new worlds. Okay, so what about arithmetic? Can we add, subtract, multiply, and divide 10-adic integers?
Yes?
Yes. In fact,
Yes!
addition and subtraction
Yes!
work the same way as they do for ordinary integers. The only difference is that the process goes on forever to the left. But that's fine. After all, when you add two real numbers, the process goes on forever to the right. For example, let's take the 10-adic integer whose digits are all 9 and add 1 to it, right to left. 9 plus 1 is 10, so we write 0 and carry the 1. Then 9 plus 1 is 10 again, so we write another 0 and carry another 1, and this just keeps happening. So the sum in this case is 0. This may be a bit of a surprise, but it means that the number consisting of all 9s is actually equal to -1. We just discovered that the 10-adic integers contain certain negative integers. In fact, you can show that the 10-adic integers contain all negative integers. They're already built in without needing to introduce a negative sign.
That's crazy cool.
We can also multiply 10-adic integers. Surprisingly, the result is 1. This means that the 10-adic integer
Because 3 times 7 is 21, carry the 2. 3 times 6 is 18 too, so yeah, that makes sense.
6's with a single 7 digit is actually 1/3. So even some rational numbers are built into the 10-adic integers.
Gotcha, that's cool.
For example, 1 over 300 has a denominator that is divisible by 10. Since we know the digits of 1/3, we can write 1 over 300 using powers of 10. But dividing by 10 squared shifts all the exponents up by 2. Since there are positive exponents now, this is not a 10-adic integer. Instead, it's called a 10-adic number.
Oh.
Real numbers can only have finitely many digits to the left of the decimal point. 10-adic numbers can only have finitely many digits to the right of the decimal point. In order to get all rational numbers, at the very least, we need to enlarge the 10-adic integers to include the 10-adic numbers. But for the 10-adic numbers to be just as good as the real numbers, we'll want to be able to divide as well as multiply. And this is the catch for base 10. We just saw that we can divide 1 by 3 or 1 by 300 and get 10-adic numbers. But can we always divide a 10-adic number by another 10-adic number as long as we're not dividing by 0? The first sign that something is wrong comes from our limit of 2 to the 10 to the n. This was the original 10-adic integer we discovered. Let's call it x. Can we divide other 10-adic numbers by x? We're going to go on a bit of a journey here, so
Can you? Because I want to say it's infinite, but it's like kind of like you can divide by an infinite decimal number. Or can you? Because we can only divide by an approximation. So I don't know. Eric. Tell me, Eric.
powers of
Please.
2 in the limit that gave x have the following property. To get from 2 to the 10 to the n to 2 to the 10 to the n plus 1, we raise to the 10th power.
Makes
As
sense.
we increase n, both powers of 2 in this equation get close to x. And that means that x to the 10th is actually equal to x. We can even check this for the first few digits by hand, by multiplying x by itself 10 times. After the last multiplication, we should get x back. Here's the first multiplication, x times x. Wait, what? We got
Pause.
x back already.
No way. That's
What?
cap. That's cap.
Some consequences, because it means that
Oh, I'm doing multiplication wrong. Oh, you got to do the whole thing and then you add it because you do this digit times the whole thing.
x times x minus 1 is 0. And neither x nor x minus 1 is 0. And here's where things really fall apart. If we could divide by x, then x divided by x would be 1, but then multiplying both sides by x minus 1 implies that x equals 1, which it's not. So we can't divide by x because doing so results in a contradiction. What we've just seen is that there are certain 10-adic numbers that we can't divide by, even though they're not 0. So the 10-adic numbers? Not such a great place to live. The good news is that this problem disappears if we replace 10 with a prime number.
Oh.
P is a prime,
Oh
and the
my
P-adic
goodness.
numbers do support
P-Adic number.
division, of course, as long as we're not dividing by 0. The reason that primes have this property is a little outside the scope of this video, but it comes down to the fact that the numbers from 2 to p minus 2 pair up with each other perfectly, so that when you multiply each number with its pair, you get a number that is one more than a multiple of p. Let's recap what we know so far. The p-adic numbers can't be organized along a number line, and they don't have the best name. But on the bright side, they contain all integers. They support addition, subtraction, and multiplication, and since p is a prime number, they also support division. Since they support division and contain all integers, they also contain all rational numbers. What about their limit points? Are there any holes in the p-adic numbers?
There's gotta be, right?
There are
Like
no holes in the
100%.
real numbers because whenever you have a sequence of real numbers where every digit stabilizes if you go out far enough, then its limit consists of the stabilized digits, which is also a real number. The same idea works for p-adic numbers. There are no holes in the p-adic numbers because whenever you have a sequence of p-adic numbers where each digit stabilizes if you go out far enough, then its limit consists of the stabilized digits. And
Bruh.
this is again a p-adic number.
Bruh.
We'll come back to the square roots of -1 in a minute, but first let's see some more nice graphics. At the beginning of the video, we looked at 2 to the 10 to the n. Now let's look at 2 to the 5 to the n.
Mm-hmm.
Rather than writing integers in base 10, now we'll write them in base 5, where the possible digits are 0 through 4. Here's some more data.
So they all
And they
seem to get closer. Okay, so yeah, this is a good question. What is it getting closer to? Is it like one of the numbers, like 1 or 2? Is it the average of these numbers? Maybe I don't get that yet.
converging. So what are they converging to?
Good question.
Well, the
I'm
limit
wondering.
is some 5-adic integer. Which 5-adic integer is it? Does it have another name? If we call the limit x again, then we can play the same game as before. Both 2 to the 5 to the n and 2 to the 5 to the n plus 1 approach x. So x to the 5th equals x. Can we say anything more? Let's square x like we did for the 10-adic limit earlier. When we add 1 to this number consisting of all 4s, we get 0. So this number is -1.
Do we? Oh, because it's a 5. It's 5. Because it becomes 5, and then you carry over the 1 because it's a 5, and then, okay.
This means that x squared is -1.
Okay.
This limit is the analog of I. It's the square root of -1. This is extremely different from the real numbers. In the real numbers, there is no square root of -1. But in the 5-adic numbers, there is. We can prove that this limit is the square root of -1 by factoring x to the 5th minus x. Since the 5-adic numbers support division, the only way for this product to be 0 is for one of the factors to be 0. The first 3 factors are non-zero, so it must be the last one. The existence of P-Adic limits
That's
like
cool.
this is actually pretty common. Let's mix things up by looking at a different type of sequence, the sequence of Fibonacci numbers.
The Fibonacci numbers. That was so bad. That wasn't even close to good.
P to be 2, and look at the 2 to the nth Fibonacci numbers. The 2 to the nth Fibonacci numbers.
I thought I was gonna make like a fake. It'd be funny if like a picture of like Shrek showed up on the numbers here.
But if we take every other row, we do get convergence.
Oh, mamacita. That's cool.
It's not at all obvious.
Or like
In fact,
inverse.
These two limits are the two square roots of -3/5. Be careful not to fall into the trap of thinking that these are complex numbers. These aren't complex numbers. These are 2-adic integers that when you square them, multiply by 5, and then add 3, give you 0.
Gotcha.
Since the 2-adic numbers contain square roots of -3/5, what about square roots of -1? In the 2-adic numbers, -1 is the number whose digits are all 1. Since when we add 1 to this number, we get 0.
Gets you 0. Yeah. Could have called that, Eric. Come on.
So what would a 2-adic integer look like whose square is -1? There are two possibilities for its last digit, 0 or 1. If it's 0, then 0 times 0 is 0. So we get a 0 in the product where we want a 1. So the last digit can't be 0. If the last digit is 1, then 1 times 1 is 1, which is what we want. So the last digit is 1. What about the second to last digit? If it's 0, then 1 times 0 plus 0 times 1 is 0, which is not what we want. So it can't be 0.
Just 1,
If
right?
it's 1, then 1 times 1 plus 1 times 1 is 2.
Oh, I'm so stupid again. Oh. He has me on a hook. He just sinks the line, and I'm just like there, and I bite it, and he's like, haha, no. And he
Write 0
eats
and
me.
carry the 1.
Also pause. These things, I've been thinking this the whole video. These little lines here. Do you guys remember that game, Slither.io? You ever played that back in the day? Let me show you. We're gonna play some Slither.io. Yeah, this game. Who should I be? I should be P-Adic. Boom. Ooh. Yeah. This is it. Look at my little worm. It's just peak gameplay. Look at eat those orbs. It's like me in math class. Oh. You need to click, right, to hold, to go fast. Oh, I'm so good. Oh, he had no chance. I'm gonna eat that, man. Oh, get this orb. This orb's good. Oh, I'm so long, dude. All right, we just gotta climb up the ranks. This guy is massive. Can I get this green guy? He's kind of looking at me. Oh, he's good. He's good. I don't want to mess with him. Low key. Let's just eat our orbs and do our thing. Eat our orbs, do our thing. Oh my goodness. You can. Okay, I thought I was gonna kill myself with that. I didn't remember you can overlap yourself. All right, let's go get like someone crazy. Let's get a big boy. Oh, he's huge. Ooh. Oh, I'm so bad. Oh, he just died too. All right, one more time. We're gonna get the biggest. We're gonna kill the biggest guy in this server, and we're gonna go crazy. All right, so we're back in round 2. P-Adic with the heroin. That guy looks kind of. All right, you just gotta get some length on us. I got some girth. You know what I'm saying? Yeah, this is what I've been thinking about the entire time we've been talking about P-Adic numbers. Just playing this game. Ooh, orb. Oh, come here. Ah! Oh! Okay, we're fine. I almost just kamikazed myself there. Oh, he knows the strat. He knows that you gotta. No, that was so unfair. All right, one more time. No, when we finish this, we're done. We're not playing this ever again. Holy heck, I'm so mad at that guy. Where are we on the map? Let's go to the center, right? Is it kind of like, you remember Dipe.io, the tank game? Anyway, is it like Dipe? Is they all like collect in the middle or something? Oh, that guy's getting coiled right now. Oh, that poor dude. You're done. Oh, he's not donezo. He's alive. Oh, I'm so bad. All right, one more. This is it for real. One more. Actually, I'm literally just chucking my computer after this one. If I die. I might never die. I might be immortal, dude. Cool. You're a bot? Oh, I didn't think so. Yeah, that doesn't look like a bot to me. Okay. Oh, he was gonna kill himself into me. Why did I leave? Dang it. All right, we got this. We're going in. Oh, you gotta stop tickling me. Stop. Oh, I was so good. Oh, give me that. Give me that. That's mine. That's my kill. Like Alex the Lion. Oh my gosh. Oh, that was so genius. Oh, he got bamboozled there. Can I start circling people? Oh, this is dangerous. This is a really dangerous place to be right now. This is really dangerous. We gotta be careful. We gotta be super careful. We gotta be careful. We gotta be careful. Oh, let's get this stuff. This looks good. Oh, no, what? No, I thought I was gonna miss him. All right, we're actually done. We're actually done. We're not playing this again. Or we're going back to P-Adic numbers. I'm sorry, guys. I couldn't win. I'm so bad at that game. Holy mercy.
This is still not what we want. So the second to last digit also can't be 1. We've tried both possibilities for the second to last digit, and neither of them worked. So there is no square root of -1 in the 2 Adic numbers.
Oh.
What about if p equals 3? Do the 3 Adic numbers contain square roots of -1? Not there either. But the 5 Adic numbers do contain square roots of -1. We saw this earlier. One of the square roots is the 5 Adic limit of 2 to the 5 to the n. Try this on your own. Pick a prime number p and see if you can build a p-adic integer from right to left whose square is -1. If you do this for a bunch of primes, you can probably guess a characterization of the primes for which this is possible. So
I'm confused. How would I do this? Like, I want to do this exercise. Let's look again. So he did this and then he squared it. How do you just get 4 here? Am I missing something? Because I'm thinking, let me write this out. Let me get my iPad. We're going to iPad this right now. Can we do the good old screen recorder on here? Okay, so let's write this out. We have 3, 0, 2, 1, 2, right? So you just copy this twice. Let's do some multiplication. So this is 4. 2 times 1 is 2. 4, 2, 0, 2. Oh my goodness, it's happening. 0, 3. Okay, and then 0, 0, 4, 6, 0, 6. Okay, so we can see. So we got 4 here. We got a 4 here. This is not 4. This is 9. How did this happen? Or if we get 4, we get 4. And this is 9. But because it's a 5 Adic integer, like base 5 instead of base 10, we start over from 5. So we subtract 5 from 9, and that equals 4 at the end. So then we do it again. 0, 0, 0. And then 1 times 2 is 2. You need to carry the 1 right here. So this is actually also 4 because it got carried over here. Dude, we're kind of cooking. We're kind of cooking. Okay, so then we just need to make a 7 Adic number. How do we do that? Yeah, so they just took 2 to the 5 to a ridiculously high number and then recorded the digits. So for this exercise, we're doing, this is all for this one exercise that he asked us to do. So we're finding an Adic number, a P-Adic number, whose square is -1, right? So let's try 7. I need a beefy calculator. You think Wolfram Alpha will have that? Let's do Wolfram. Wolfram Alpha. Wolfram Alpha. Okay, we're gonna do 2 to the 7th to the 5th power. This is a huge number. I didn't realize. Okay. Oh, we found it. We just need 8 of these. Okay, I think this is it. So we have 8, 2, 2. Okay, let's multiply these together. So we have, okay, this is going to be 64, 6, 6 to 8, 16, 22, 8, 9, 8. Okay, so we're going to add all these together, base 7. So we have 4. Okay, that is clearly not, so this is not -1 because adding 1 does not change this to 0. So I don't know if I did that wrong. Hopefully I did that right. I just followed the same process before, but if I didn't, I'm so sorry. So from what I assume from the work I did, I don't think 7 Adic has a -1.
If you do this,
or square root of x squared is -1. Okay, so yeah, let's do a final recap right now. I just want to make sure I understand this to the fullest. So let's talk about what is a P-Adic number. A P-Adic number seems to be, so as these numbers get infinitely large, they converge to something, and that's the P-Adic number. We talked about the P-Adic absolute value, which shows how close a number is to 0 or how large it is by dividing by the highest power of that P-Adic number. So we talked about how 78,000 is a larger number because it's actually only 1 over 1,000, where this one is 1 over a billion. And then what else did we go over? We went over the multiplication, right? We multiplied this P-Adic number to show how that equals, what is this one? This one's -1 because if you add 1, it equals 1. And then we did that exercise. So yeah, that's what a P-Adic number is. And I think I understand kind of well what it is. I think I'm missing a lot, but I think that's just the base intuition. So there we go. We figured it out. Finally. Oh, dude, I'm so sick of I'm glad I figured that out because like quaternions sucked. That took like 4 videos and I was just dying and I still don't understand them. These ones I still kind of don't understand, but like I feel like I gave a pretty good synopsis of what was going down. So anyway, thanks for watching.